No time to waste here. Let's jump into orbital diagrams. Let's write the orbital diagram for sulfur. And we want to determine the number of unpaired electrons as well. If we look at sulfur on the periodic table, it has 16 electrons. Orbital diagrams, by the way, we are never going to have a noble gas core for an orbital diagram. We're always going to write out the entire thing. So to write out this orbital diagram, we're just going to start writing in boxes for each of those sublevels. So we're going to start with the 1s. And by the way I do this is I write in a whole bunch of boxes up to the point where I don't think I need any more, and then I go back and fill in the electrons. So I don't fill it in as I go. I don't say, okay, 1s, put in the 2 electrons, 2s, put in the 2 electrons. I write a bunch of boxes and then go back and put in electrons. I think that's a safer way of doing it. It's easier to keep track of how many electrons you put in that way. So we have 2s. After 2s, if you remember, comes 2p. After 2p is the 3s. After 3s is 3p. After 3p is 4s. And I think that is plenty of boxes. I believe. We'll see. So again, 3p has 3, or any of the p subshells have 3 orbitals. The s subshells have just a single orbital. And so if we just go back here to the beginning, we have 16 electrons to put in. So 1, 2, 3, 4, 5, 6, 7. Notice that I put them in singly first with parallel spins. Even though I know they're going to get paired up because I still have plenty of electrons to give, I'm still going to go ahead and do it properly. Put them in one at a time with parallel spins. So that was 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I am out of electrons. So I had to pair up 1 electron here, and I didn't even have to use the 4s, but that's fine. It doesn't hurt to draw an extra box. The 4s subshell is there. It exists. It's just empty, like I've shown it. So if anything, it's even more accurate. So take that. I'm just kidding. So you could just erase that if you wanted to, but I'm just going to leave it. So we have this as our orbital diagram, and we have 2 electrons that are unpaired. If you had not followed Hund's rule, you would have had 0 unpaired, because you would have put 2 here and then 2 there, and you would have had just an empty orbital here, and that would be incorrect. Remember, singly first. Put them in their own individual orbitals, and then pair them up. Alright, so that is sulfur. Let's do a couple more here. So fluorine has a 9, if I remember. Yes, 9 electrons. And magnesium has 12. We've actually seen magnesium already, although not in its orbital diagram. So with fluorine, we have the 1s. We have the 2s. We have the 2p. That should be enough. We have 9 electrons to put in there, so 1, 2, 3, 4, 5, 6, 7, 8, 9. That is the orbital diagram for fluorine, and we have 1 unpaired electron in fluorine. For magnesium, on the other hand, with 12 electrons, so again here starting with the 1s, 2s, 2p, 3s, 3p, and that should be plenty. We might not even use that 3p. We have 12 electrons to give. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we did not, in fact, use that 3p, which again is perfectly fine. So that is the orbital diagram for magnesium. So it is the same overall process as what we did back here for the electron configurations, except now instead of just showing these subshells, we are actually showing the individual orbitals inside of them and the electrons in those individual orbitals. So it's more detail. All right. I promised you in, I guess it was 2 videos ago, that we would come back to valence electrons. Just to remind you of what we said about valence electrons back then, these are the highest energy electrons. These are the ones that are farthest away from the nucleus, and that's actually more important than just the highest energy. They usually are the highest energy, but technically speaking, they actually don't have to be. They just have to be the farthest away from the nucleus. The way that we determine which ones are farthest away is by what their principal shell number is. So all of the electrons that are in the highest principal shell, the highest occupied principal shell, are valence electrons. All the rest of the electrons are core electrons. So for example, back here in fluorine, the highest principal number that we got to was 2. We had stuff in the 2s and the 2p. So both of those are in the principal shell 2, the second principal shell. So both of these have valence electrons. All of these 2s and 2p are valence electrons. We have 7 valence electrons. Yeah, 7. Sorry. It's late. I'm miscounting things. 7 valence electrons. 2, 4, 5, 6, 7. And then magnesium, we have stuff in the 2s and the 2p, but that is not the highest occupied principal shell. We have electrons in the third shell. We have 2 electrons in the 3s. There's none in the 3p, but we do have 2 electrons in that 3s, and so magnesium has 2 valence electrons. And all the rest of these are core electrons. So core and valence, those are the only 2 kind of electrons that exist. And one of the most important factors in the way an atom behaves, both chemically and physically, is the number of these valence electrons. How many valence electrons does it have? The reason for this, which I believe, okay, I guess I don't get into that there. The reason that these are the most important electrons in terms of its chemical and physical behavior is because these are the only electrons that can interact with other stuff. Because these electrons are the farthest away from the nucleus, if we have an atom here, sorry, that's a terrible circle, but pretend that's a circle, and there's some other atom here, and they're going to interact with each other, this atom is not going to interact with the electrons that are way down in the core of the nucleus, near the nucleus. It physically cannot interact with them. There's stuff in the way, and the stuff that's in the way are the valence electrons that are sitting out here on the outer edge of the atom. So the only electrons that interact with other stuff are those valence electrons. And so those valence electrons are what determine its chemistry, determine how it behaves. So that's why we care about valence electrons. The core electrons are important too. They have to be there, otherwise you wouldn't have the other valence electrons, but they don't really do much in terms of chemistry. They're like a foundation that the valence electrons sit on. So in germanium, for example, germanium has 32 electrons. we're going to go ahead and write the full electron configuration for germanium. So we're going to start with 1s, which has 2, 2s2, 2p6, 3s2, 3p6. After the 3p is 4s, not 3d. 3d comes after 4s. Let's see, I think we're up to 30 now. So that means we have 2 more to give into the 4p. So if we look at this configuration, what is the highest occupied principal shell? If you said 4p, you're only half right. The half that's right is the 4. The 4p is not a shell. 4p is a subshell. The 4 is representing the shell. So we actually have 2 different subshells that are both in the 4th principal shell. And so in germanium, we have 4 valence electrons. Even though the 4s is lower in energy than the 3d, which is what the order here is representing, the 4s is lower in energy than the 3d, it is farther away from the nucleus. It's lower in energy because the shape is simpler. It's a more simple shape, just to put it in as basic terms as possible. Because the spherical shape is a very simple shape, it's lower in energy than 3D, which can have much more complex shapes. And so even though the 4s is farther away from the nucleus, it is lower in energy. But it is still going to interact with other atoms way before those 3D electrons do. And so these 4 electrons, the 2 in the 4s and the 2 in the 4p, are valence. And then all the rest of these are core electrons, including the 3D. All right, hope that makes sense. I think we'll leave it there for this video. In the next one, we will pick up with, well, this here we actually have already kind of gone over, so we'll just very briefly review using the periodic table to work out electron configurations, and then we will jump into irregular electron configurations. So I'll see you all in the next video.